Awesome, everybody. All right, starting on the first page of notes, we're going to just do a quick 5-minute, where have we been to kind of get our brains back, because I know fall break, even for me, I forget, what am I doing with my life? Okay, so the very first thing we did at the unit is we drew a picture, so look at that picture, everybody, of a solid versus a liquid versus a gas. Okay, if your hands were to represent molecules, show me a solid. Show me a liquid. Show me a gas. Perfect. Okay? Then, the next day, or the beginning of it, and that's really the idea of our whole unit. This unit is all about solids, liquids, and gases. Understanding them from all different sides of our chemistry triangle. We've covered the solid side. The solid side deals with ionics and how, they're not malleable and they have high melting points because of their structure. Same thing, metallics. We talked about a metallic structure and why they are malleable and they conduct electricity well. Okay, covalents, we had to spend a lot of time on those because they can vary. Right? We have covalent network solids, which are diamond and crazy strong. But then you have the covalent molecules, which are most things on Earth, and they can be all over the place. Right? They can be malleable or not malleable, and because of that, it's all about their intermolecular forces. So that's kind of where we went next. So flip your page over. Okay, so we open the next page. So the next one is that we introduce intermolecular forces, which we have 3 types. We have the London dispersion force, which what type of molecules have London? Everything, because what causes it? Electrons, and everything has electrons, right? The next type of force is the dipole-dipole force. How do I know if something has dipole-dipole? It has to be polar, right? Okay, you got our little models up here still. Okay, and then the final type of force was the hydrogen bonding force. What do I look for with hydrogen bonding?
It has hydrogen.
Not, right? N or F with an H. Okay? These intermolecular forces, once again, help us understand covalent properties because of how strongly or weakly it holds. Right? So keep in mind, this is the intermolecular force, is that magnetic felt between them. Okay? If it holds it tightly, last time, so flip the page again. Flip it to the next page. Last time what we did is we did a series of demonstrations as we talked about these types of properties. Actually, flip it again. I guess that next page was just practice problems. So last time's lesson was all about the application. Some of you I know were gone. If you haven't yet, make sure you do watch the lesson video. That's how you make up your engagement points if you're ever absent. Okay? And we had the white paper with our demonstrations that we did. The demonstrations were connecting properties to IMFs. So one of them are we played with those little hand boilers. Remember those colorful liquids that you held in your hand and some of you were zombies and doesn't work for? Okay? So what was the connection there with IMFs and boiling? What connection did we find? Something has a high boiling point, what would that tell me about its IMFs? And their IMFs must be strong, right? So it's a direct relationship, right? Because if this holds strong, it's going to take a lot of energy to pour it apart. So IMFs are kind of what transferred us into the liquid conversation a little bit, because IMFs deal with liquid things turning into gases, right? Vapor pressure, boiling point. It can deal with solids as well, right? Melting something, but it also brought in the liquid side of the solid liquid gas conversation. Okay? Today we're going to finish up. We had 2 properties we introduced last time. But we didn't get them to all the way. I think I ended on this, if I'm right. Is this where we are picking up?
Yeah.
Everything up to that is filled in. Okay, so we're going to finish up this little conversation about some properties of IMFs, and then we're really going to take a different turn and talk about gases. So now we've done solids, liquids, now we're going to spend the next few days understanding gas properties and what goes on there. Okay? All right, so with this idea of these 2 properties, okay, these properties, so boiling point, like we mentioned, was all about strength, right? The stronger the force, the higher the boiling point is going to be. When it comes to solubility and being miscible, this one isn't so much about strength as it is the comparison. Because in these properties, you're bringing 2 different things together, right? So solubility is the ability to dissolving. You may want to add that solubility refers to a solid in a liquid. Okay, so a solid in a liquid is solubility, but a liquid with a liquid is being miscible. They're really one and the same of why they happen. You just don't usually use the term soluble if you're talking about 2 liquids. Just like you wouldn't use the word miscible if you're talking about salt and water. Okay? demonstration here to talk about this. Sorry, I'm gonna go grab a beaker really quick, but I have an extra one.
Do you think we have time to fill in the board?
No way.
I kind of draw it through character.
So, sorry for the interruption, I come back and try to So, a great example of being immiscible. So, immiscible, by the way, is the opposite of being miscible. So, miscible means that they mix. Immiscible means they do not mix. Okay, a great example that we're very familiar with is oil and water. Okay, so I poured some water down here. This is vegetable oil up top, right? And they don't mix with one another. So we'd say that these two things are immiscible. Okay, now first off, you need to recognize that some students would be like, oh, they don't mix because of density. Okay, if that were true, if I shake it, so this is the same thing just in a jar. Okay, so if I shake it, if it was about density, then it wouldn't really separate back out. Or would take a very long time for it to separate out. When it deals with their actual forces, it separates. Okay? I saw a hand.
Oh no, I was gonna ask if you can just say not miscible too.
You can, yeah, you can say not miscible if you're like, I can't remember what that is, what it is. Okay? So notice how it separates back out. So this idea with intermolecular forces comes down to a phrase that it's kind of a thing you can use to help you remember it. I wouldn't use this phrase like just as a standalone thing on an FRQ justification. I'd obviously give more detail, but it can help you remember that it's like dissolves like. So things that have similar forces can dissolve other things that have those same forces. For example, polar versus nonpolar. If a molecule is polar, it's able to dissolve or mix things that are also polar. If it is nonpolar, it's not going to mix with things that are polar. So like to like. Polar will dissolve polar, nonpolar will dissolve nonpolar, but if you mix the two, that's what we get. Water is very polar, right? Has hydrogen bonding, dipole, London. Oil only has London dispersion forces. Okay? The idea here is that the water, because of its forces, is holding on to itself, right? They're good buddies. Strong friendship force going on. Okay? Oil has completely different forces of London. If they're going to interact, there has to be something that's going to attract them to come together, meaning their forces have to be similar. Otherwise, there's no reason. So if this represents like our oil and this represents our water, right? This is holding very tightly to each other. Is this one holding tightly? Not really, right? It's London. But there's no reason why this would happen. Unless this thing had enough force to like trade it. So that's the idea of the like to the like. Alex?
So from there, is that where density plays a role in like oil ends up on top of water instead of not below?
Yeah. So the density is like where they lie, but the fact of them not mixing goes down to their forces. Yeah, good connection there. Yeah, Zach.
Why does non-polar like substances dissolve other non-polar substances?
Great question. So if something is non-polar, so I think this is another unit that things naturally will mix unless there's something stopping them to. And so if everything is London, they all have the same strength at which they're holding, and so then it just naturally is going to spread. There's a property called entropy that we'll learn about in another unit of this natural order of things to always spread out if they can. Does that answer your question, Zachary? Yeah, great question. I'll snipe you that. Okay, other questions before I do a demo for smiley face and you're gonna write on your board? Okay, as a table, you're gonna write me a claim with evidence and reasoning based on the properties of, where did you go? Food coloring. I lost it. Root red food. Okay.
It's because there's a dead.
So your claim should start out as red food dye has blank IMF forces because of what evidence do you see to prove that? So you're trying to come up with a claim on the IMFs of the red food dye based on the observations you're about to see. Everybody ready?
No.
Okay. So pick someone to be the scribe. Obviously you should discuss it as a table. Okay? Alright, I'm going to drop it in. Alright, dropping in the red food dye now. Observe. Because it's the problem. They'll kind of go really slowly. It's like a lot.
Oh yeah, because it's
It's part of like the surface tension of it, right? You have to kind of really Okay, write me a claim about the IMFs of the dye. What can you claim about it and why? You got 2 minutes. Come up with something. That would be what it is. You can, so something that does not write in body, like just better in water, but there's still. All right, you got 40 seconds. Give me an answer on that board.
I feel like that makes sense.
Stop it. Read it.
Oh, you can say water.
All right. 3, 2, 1. Show me your board.
Show me the board. I literally need to show me the board.
Time has mixed with oil, but it has, but it mixed with water. Just oil is high and water is high. Yes, I did. You took up a jillion years.
Question out really quick. I'm gonna have 2 groups read it. Everyone is correct. Once again, to help improve your own justifications, it can be valuable to hear how people said the same thing you did, but in different ways. Not saying there's anything wrong with the ones I'm not picking. I just want you to hear it in a variety of ways because that solidifies it and helps you get it. So Bryson, will you read what your board says for everybody?
Okay, so I said the red food dye has high IMFs because it didn't mix with the oil but with the water. This is because the oil has low IMFs and the water has high IMFs, in which we saw the water mix with the water and not the oil.
So this group's table is perfect, like their logic is spot on, but there's actually 2 words I would change and avoid using when it comes to solubility, because it can just be a little.
Do you want to get rid of mix?
confusing. Not mixed, it's saying high and low.
Oh.
Because high and low can be relative terms when it comes to IMFs, right? Because sometimes dipole is, does that make sense? Because there's that overlap. So can you think of a different, I love everything you said, but can you think of a different,
Would Porter be right in saying polar and non-polar?
there you go, just label it. Yeah, and other people did this as well. That's why I picked on them to read, because some of you others I also know to use that word. So I wanted to make sure we're aware of that. Thank you though for sharing how to extra smiley face that table. And then this table. Okay, everyone listen to Lily. She's gonna read hers.
I said red food dye has strong IMFs because the oil wasn't able to mix with it since it's non-polar, but it did mix with the polar water. That shows that the food coloring was polar and had strong IMFs.
Good. So same thing. Take away the strong, but bringing in the connection idea. You are where I put my camera. So then I'll figure out what we're gonna do with this thing today. Questions on this? Anybody? Does that make sense? This idea of solubility?
Yeah.
Okay, move down to the question below and try that out with your table buddy. I've given you 3 compounds. You're going to tell me which substance would dissolve better in water or carbon tetrachloride. So you're picking between 2. Oh, don't apologize. I just am experimenting. How's that? Is that okay? Is that annoying? Okay, I think I'll get like a little but then it doesn't have to be like, but I like how that is there now.
Has London forces.
So it's pretty much like one of these, all chlorine. So this is carbon tetrachloride, by the way. CCl. So you're picking between water or carbon tetrachloride. So it is a tetrahedral, but they're all chlorine. Which one would dissolve that substance best?
So because of their polarities, they're going to
So
mix
underneath each molecule, you should write 102 either write water or CCl4.
So wait, the first one's tetrachloride. What's their guys'
I do.
I mean, you can get like partial soluble where like if you have some, you know, like when things have like lots of London that can be quite strong. Like those ones could be partially dissolved, but you're not going to have. So I wouldn't worry about exceptions in the other Okay, let's check our answers and then we'll move on to our next topic. So the way you should think through this, which I heard us do, is it's about you got to compare similarity. So I have to know what forces do these have, what forces do those have, and do they match? So really, in big terms, you really can just look at polar and non-polar because that's kind of the dividing line. Obviously, something else that's polar, even if they both don't have hydrogen bonding. So this substance, CCl4, is nonpolar. Water, we know, is polar, has all the forces. So the first one, so you can have a smiley face for each one of these you got right. You should have said that this would dissolve best in CCl4. This one would dissolve best in water. And this one would also dissolve best in water.
Yippee.
So up to 3 smiley faces. Questions on solubility or miscibility, identifying it? Okay, one final just thought question, and then we'll move on. Okay, don't say anything out loud. I'd like you to think to yourself. But it's often a common phrase where people say that water and oil repel each other. Now that we've learned what we have, do you agree with this statement? Nope. Why? Don't say anything out loud. Just think to yourself. Do water and oil repel each other? Is that a correct description of what's going on? Because what? Show me with your hands. What do you visualize with the word repelling? Like pushing against each other. Do oil and water push against each other? Then why don't they mix? Yeah, there's no attraction to pull them together, right? Water holds to itself, and it doesn't want to let go to let the oil in. Because oil would also have to have forces as well. So just kind of something to recognize, like there's really no repulsion going on ever. It's just a difference. They're just different forces, so they don't mix. Okay? All right, any final questions on this before we move on to gases? All right, so let's talk about gases here. With gases, with everything, right, we want to have a visual at the molecular level of what's going on. So I'm going to tell you a little story about Miss Alviso as a child. This is what I always think about when I visualize gases. Okay? So when I was in elementary school, for whatever reason, I collected bouncy balls.
Who didn't?
Maybe others did too, like, I don't know, but it's just something I did. And so I'd always, anytime there was like themes, I just collect them, I'd ask for them for like my birthday. So I had like a collection of like 250 bouncy balls. And they were like different sizes and colors and like, you know, like a collection.
Take them and just like
I should
dump
do
them
that.
off a really high place.
So one of my favorite things to do with my siblings is we'd take my big collection, we'd go into the bathroom because it was tile, we'd close the door and plug all the holes of the bathroom, and then take the big box of bouncy balls and just throw them on the floor. So they just go like, and we're just standing in there getting pelted by bouncy balls.
Yeah.
Because we just thought it was the funnest thing ever. We do it over and over again. We sometimes do it with the lights off. Make it real extreme, right? But like this is what I visualize when I think of a gas molecule. Obviously never losing momentum, but they're bouncy balls in a container that are constantly moving, constantly bouncing off the walls, everything around it, okay? That's what I encourage you to visualize something like that as we talk about gases. Now there's 3 units measurements that we deal with gases that we need to have a really solid understanding of because they'll come up a lot. So the first one is pressure and understanding what pressure means. So pressure is about force and area is that second blank that kind of is hard to read. Okay, so pressure is about force and area. So it's how hard are they hitting the walls, but also how often are they hitting. So there's 2 factors that can influence pressure. Keep that in mind. That means we can influence it in 2 ways. Right, like I can change one thing and it's going to make pressure go up, or I can change the other and it'll make pressure go up. Okay? Pressure units, the main ones we'll use are ATM and torr. That's the measurement unit. So we'd say like this thing has a pressure of 1 ATM or 760 torr. Another one is called a kilopascal. It's a lowercase k, capital P, little a. Once again, these are just units of measurement. Okay, so when you see this unit, what you need to recognize is, oh, that's a unit for pressure. Okay? Keep in mind, once again, it's about how hard and how often they're hitting. Okay? Second one we'll talk about a lot is temperature. Keep in mind, chemically speaking, don't think temperature as hot and cold. Because hot and cold are completely relative terms to what you're talking about. Okay, temperature is a measure of the average kinetic energy of the molecules, which is their movement or speed. So it's telling you how fast or slow the molecules are moving, is what temperature measures. So if temperature goes up, the molecules move faster. If temperature goes down, the molecules move slower. Okay? Now keep in mind that it's an average. Okay? So you can have two things that have the same average, but their distributions can look very different. Right? Just like in a class like A1, like B6 and B7, you actually have the same averages on the test, but the scores could still be quite different to get there, right? Okay? The main unit we'll use is Kelvin, the Kelvin scale. It's symbolized by capital K. Fun fact, you don't use the word degree when you're using Kelvin. So you say 100 Kelvin. You don't say 100 degrees Kelvin. You don't use the degree sign. Celsius is what we'll typically measure in, but we'll always convert to Kelvin because Kelvin scale was designed based off this idea of movement. So 0 on the Kelvin scale is the point at which molecules aren't moving.
Oh.
So that's what 0 Kelvin is, and there's no negatives. So the Kelvin scale is designed theoretically to not have any negative values. Because when you do math, you throw in a negative number, it messes up things mathematically if it's negative. So that's where Kelvin is very helpful. Okay? So it's obviously very, 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 very cold to get to absolute 0 is what 0 Kelvin is called. And why I say theoretically there were no negatives is because about 5 years ago they went below the Kelvin scale. Things went weird. That's all I can say. It's like stuff I don't even understand. It kind of like, if you know anything about like dark matter in the universe, and like black, like it did weird things when they went below us.
Dark hole.
I don't even fully understand it, so I
Wait, so
can't.
there's not a way to stop, they just
You know,
stop moving
that's
forward.
science. You think there's a limit, and then they push back. Okay, final piece of this, everybody, is volume. Okay, key thing with volume we need to understand is a gas always occupies the entire space of the volume. Okay, unlike a liquid, right? Like if I use this, so this beaker is a 250 milliliter beaker. But if I use this for a liquid, it doesn't mean the liquid's at 250. It depends on where the liquid goes. But if I fill this with a gas and seal it, the volume of the gas is 250. No matter how much gas I put in there, they always occupy the entire space of it. So whatever the size of the container is, that is the volume of the gas, because they fill the space no matter what. It's actually quite amazing how much empty space there really is between gases, because we don't experience that. Like to us in this room, this seems to be filled with lots of air. In reality, it's actually really not that much. Like we could gather all the air molecules in this room, so imagine all the tiny little bouncy balls, and they would fit in a box like about the size of this ceiling tile and a foot deep. Like all the bouncy balls in this room could fit in there.
Wow.
But while I'm walking around, it's not like I like hit an air pocket where it's like, oh, there's no air in this space, right? Like it just seems to be everywhere at once, right? So kind of okay. And then liter is our main unit. Okay, exactly. Okay, so as we talk about gases, our first step here, so we are going to, IMFs didn't really have much, there was no mathematical side to them. The gases is, we are going to hit some heavier side of the mathematics in connection to chemistry here. So the idea here is this equation we're about to look at is based off the fact of gases behaving ideally. Okay, now obviously they don't always behave ideally, but as long as they do, this mathematical equation works. But if they are really not ideal, then this math equation actually fails. And it doesn't give you the right answer because it's not behaving like a gas. So the two things that need to be happening for it to be ideal is number one, they need to be moving in such a way that IMFs never really happen. Okay, which makes sense because if these two things are flying around the room, right, two water molecules, right, if they're flying around as gases, as liquids they normally could link up. But as gases, the assumption is that they're just moving so fast and so much, they never have a chance to link. So IMFs are like non-existent for gases is what we're assuming. The other thing is we're assuming that the bouncy balls themselves don't occupy space, which is false. They do, they're obvious, but we're just saying they're so small in comparison to the space they're filling, we're assuming the volume doesn't matter. Allie?
Is there a possibility they could ever link up? Or is that really?
Yeah, totally can. And the more, and we'll get to this in some other days too, like if certain properties change, then they're more likely to be less ideal and do things like that, for sure. So it's kind of, it's almost a theoretical thing to say like an ideal gas, because like never happens. But the math works out. In this class, anytime you have to use it, it's going to work out. But like in an experimental case, you might have to change your settings so it behaves more ideally. Does that answer your question? Okay. All right. So today's our first experience of, we're going to learn the equation that's on your formula sheet. So I gave you a formula sheet at the beginning of the year. We haven't really ever used it, but now it's going to become valuable to you. So if you know where that is, you can pull it out now so you can relate to it. If you don't, maybe look off a neighbor. Okay. So it looks like this. It was like with your periodic table.
I know, it's so heavy. Let me try to recreate it. It's in there.
So on the AP exam, you'll get one of these with your periodic table to use. So we don't need to memorize any of this. We just need to know how to use it to help us. Was anyone else absent maybe that day and you don't remember the timeline? Okay.
Mole to the -1 power. Kelvin to the -1.
So flip your formula sheet to the back page. Flip it to the back page. There's a category that says gases, liquids, and solutions, right? Which is the unit we're in. Okay, the first equation that we're looking at there, you can write on this, by the way, this is yours, so if you want to put any extra notes to remind you, obviously you recognize on the AP exam you're going to use the one they give you, so you don't get those notes, but if it helps you, you're welcome to write on this. Okay, so we have the ideal gas equation, which is Pp equals nRT. Pressure times volume will equal moles times this gas constant times temperature. Okay? So I want to point out as we get familiar with our formula sheet, so the formula is there right at the top, but then notice to the right, all the variables are defined for you. So you don't even have to like memorize what is n equal, what is, like what are these things, like it's right there for you. You just need to know how to use it. Okay? With this, so P is pressure, V is volume, N is moles, don't ask me why. R is the gas constant, okay, which is on your formula sheet. So look on your formula sheet. Under the variables defined, see R equals, does everyone see that on their formula sheet? I also gave it to you in your notes, but I apologize, I gave you a table that's more complicated than it needed to be, because there's only ever 3 R values we're going to use in this class. Okay, so R is a constant like Avogadro's number, but depending on the units of your problem, you will use a different R value. Okay, so if you want to make a note here of this, that you pick the R, so of all the different R's it can be, you pick the R based on the units of the problem. Okay, so depending on the units of the problem, you pick which R value will fit. Okay, so let's try an example. Any questions on this before I try an example? Yeah, chat.
So we don't need to memorize all 3 of those, because we'll have access to them.
Yep, they're just off, so like here's the formula, and then down here, it has all those values. Yep, so you'll have that with you. So don't waste your time memorizing it, because you'll have it too. Okay? Alright, let's try this problem.
Bye-bye.
So this problem says, as I read it, something I always do with problem solving is I underline units as I read, to kind of like see what are the different things they're giving me. Okay? So we have calcium carbonate, it's decomposing upon heating to give these 2 substances. A sample is decomposed and the carbon dioxide is collected in a 250 milliliter flask. So what unit is that one telling me? Milliliters, which means volume. Alright, so this is my volume amount. Okay, the gas has a pressure of 1.3 atm and a temperature at 31 degrees Celsius. I always circle what I'm trying to find. How many moles of CO2 CO2 are generated. Okay, so I have given information, unknown information. Let's use your equation again. Okay, so I have the normal equation of the PV equals nRT. Okay, what value or what variable am I trying to find in this problem? Yeah, n, our mole value, right? So what I choose to do is before I start plugging in numbers, I rearrange this so that n is by itself. So I have an n equals equation. So using algebra, how would I get n by itself? Yes, so I'm going to divide by RT, so I'm going to have n equals PV over RT. I find that it's much easier mathematically to just move a few letters than to like put in numbers and then start trying to move them all around. Okay, questions on how I got from here to here? Alright, so now I can just start plugging them in, but the biggest thing is units. You've got to make sure that all the units match, because we only want one unit in the end. What's the one unit we want in the end? Moles. Okay, so pressure is an ATM. Okay, so I'm going to take in, so that's P, so 1.3 ATM. Okay, the volume is in milliliter, but if you look at your R values, what unit is the volume always in? Liter. Right? It doesn't matter which R it is, they're all in L's. Does everyone see that? Okay, so I need to switch it close. Keep it going. There you go. So liters to milliliters is 1,000th of a difference. So you go 1, 2, 3. Okay, so 0.250 liters is my volume. Okay, so once again, I just had to convert the unit to match the R value. The R value is what's dictating. So in picking the R value, I want to pick the one with ATM in it. Once again, so looking at your list, the first one is joule, mole, and Kelvin, so that's not the choice I want. The second one has, liter, ATM, mole, and Kelvin, so that's the one I want. So I'm going to use the 0.08206. Oh, I already forgot what I just said.
08206.
Thank you. Now the units for R are really messy because it's designed to like get rid of everything you don't want. But if you put them all in there, it can really help you with what you're doing. Right? So the units are ATM times liter over, the reason why it's like mole to the -1, Kelvin to the -1 is because they're like on the bottom of the fraction. So mole, Kelvin. So these are all the units for that R value that I just took from the formula sheet. Okay, because the formula sheet had it like this, 08206, and they have ATM, liter, and they wrote it as mole -1,
Fraction and a fraction.
Kelvin -1. So this is the same as that, because a negative exponent, I don't know when you learned this in math, but it goes on the bottom.
Negative x.
Alright, so -1, so the powers to -1 go on the bottom of the fraction. Everyone good there? Okay, so temperature is our last variable to plug in. Based on the R, what unit does it need to be in? Kelvin. It's given to us in what? Celsius. Look on your formula sheet under that same, is it that same section? Yes, same section, and it gives you the conversion. So how do I convert from Celsius to Kelvin? Yeah, so we're going to add 273 to get it into Kelvin. 304?
No, I said first.
Okay, so there's my R. I know it's more writing to write all the units, but units can save you to make sure you don't make mistakes. Because if I have my units in there, this is what should happen before I even do any math, right? The way units cancel is they're on the top of one fraction and the bottom of another fraction. That causes them to cancel away, they divide out. So ATM is on top of this fraction, and that ATM is on the bottom, so those cancel out. Liter is on top, liter on the bottom, and And so those cancel out. Now Kelvin is on the big bottom, but this Kelvin is on the bottom of that one next to it, so they're still diagonal. And what's the only unit that didn't cancel? Which is the unit I want. If they don't cancel, you set up something incorrect. And then you can maybe backtrack your work from there. Okay? At this point, your calculator would do all the heavy lifting, because you would just do this times this, divided by, this has to be together though. So this times this divided by parentheses, this times this. Practice typing that in your calculator right now to make sure we can do it right. If you do it right, you should get 0.013. Yeah. Yep. Practice typing it in just to make sure you know. It's the worst when I see a student who's like set up the problem right, but then they get the answer wrong because of the calculator. It's very sad for both of us. So let's just make sure we don't make any little mistakes with that. Let me know if anyone's having issues and need help while you're in. Any general questions before we try another problem using this equation? So this is the R value, right? Like this is P, this is C, this is R, and that's T. Yeah. So it's just one of those constants that you have to pay attention to. Does that help? Oh, sig figs. So 1.3 is 2 sig figs. And so zeros in front don't count. It's funny that it's 3. Any other questions before I have you try for the first time? Okay, I'm going to have you skip this one and go to the next one. So go to exercise 3.4C and try this one as a table for a smiley face. Okay, bring this home.
Okay, so PV is equal to nRT. Pressure is equal to pressure. So P is equal to nRT. Pressure is equal to how many moles? 1.8
Once you, as a table, once everyone has the answer and understands it, put your final answer on the boogie board, and then I'll come check it.
Yeah, we can probably choose. Let's just do it.
So then we go to the R sequence, so we're calculating pressure ACL. It's volume. Is it 62.26?
Okay, and then that's over the volume is 60.
R, what's the volume?
3.4.
R is
Yeah, silly goose.
we're, so it's 62.36. Pressure.
I'm using the first one.
So
So it's not good one.
I'm calculating the pressure.
Okay, so basically, so let's slow down. And we're looking for pressure. Okay, so R, we just chose the same one we did last time, but LATM.
So you can choose which one. I'm using the first one. Okay.
We did that because we kind of just choose whatever we want.
That one, this one's calculated for
Well, the last one we used has.
Once again, think with the R value. The R value needs to cancel out all the units you don't want. If it doesn't cancel out the units you don't want, then maybe rethink your R choice.
So we're just, since this has meters, this has meters, that's what so really we could choose. Yeah.
Because there technically are two plausible answers for this, depending on what unit you have your.
What is with that seven?
Yeah, you can like theoretically
almost like the label.
Once again, once everyone at your table has it and you feel good about it, put it on the board. That way I know you're done thinking about it.
You have the height you remember now. Oh no! I think I do that all the time.
Did you push the button?
Yes.
Watch this. It's red. So you can't clear it. What is this one?
It's kind so it's not like, yeah, it's like calibrate the pressure it would just put you in. So there's like a few you can do to set it up. But after I got them, I was like, I shouldn't have to worry about that option. So, okay. Okay, check. Almost there? Oh, okay, good.
Not that way. Check, that was good.
Check.
Look at that. Look at that. Look at that.
Yeah, just the molecules themselves are yeah, 'cause like both of them, like they're both in the air now. When we hit, they just react to each other. Yeah, there's like not that much. There's just the oxygen, but there's not that much. Be ready to be happy. Questions for now on the ideal gas law, PV equals nRT? So just a disclaimer, because I might. So when I learned this equation in college, and I don't know if this is, I don't know if other people call it this. I guess I should ask more people. But I learned that there's like a nickname for it, so I might call this by its nickname, just out of like habit. So the equation is PV equals nRT, right? So when I was in college, I didn't come up with, like, a professor taught me this, but we call it the perf nerd equation. Because if you like kind of read it from like perf nerd.
What?
So just know if I say that, I'm just saying this like when I say this, look at me like, what are you talking about? That's just like the name of this equation. Okay, so the next place we're going to go, here's just a brief introduction, is getting into the conceptual side of these properties, okay? And understanding how they're connected. We're going to come to this middle box first here, but just give me about like 2 minutes left, okay? So what we're looking at here is understanding the connection between these properties from a conceptual side, as well as the mathematical side, of like, as one changes, how does it influence the other, and why? They're very logical if you visualize those bouncy balls, and so try to think about that. Okay, so the one I'm going to do today, just to leave you with something fun, is we're going to do the middle one of volume and temperature. Okay, so we're saying that the other ones are being held constant, right? Like we're not changing how many moles there are. We're not thinking about what pressure is right now. Okay, but just those 2 factors. Okay, so my question for you is, if I have this balloon, right now it's at this temperature in the room and this is its volume, what's going to happen to its volume if I decrease the temperature of the molecules? Talk at the table really quick and decide what's going to happen.
It's gonna.
And we'll test your hypothesis.
Oh wait, no. Yeah. Wait, why I feel like if it gets warmer,
Okay. Okay, are we ready? We're going to test it before you leave. So I have a balloon. I'm going to use liquid nitrogen to cool it down. Okay? We'll be real quick.
I'm gonna miss English.
I don't.
Okay, sorry.
Goodbye.
You can gather things and look at it as you leave.
It's classic.
I need it more. Remind me and I'll do it again at the start.
I don't know. I think we have
But I need it.
I don't think it's a makeup.
But why is it called liquid?
I'll do it again at the start next time so you can see a little bit better. I didn't pull it up in. I'll do it again on Friday when we're a little less rushed. I'm really excited.
Put up your chairs. Keep up the ball.
That's because it evaporates.
You're physically giving me pain by making me laugh.
Yeah.
No,
It's like
laughter is not the best medicine.
No, why did they say it?
Because
right? The difference is because it evaporates so quickly, so like if you
Order, I hope you chip
put
your.
your hand in it, like, can I put my hand in it? But like if it just like hits you, like it evaporates so quick because of the forces that it like feels cold, but then you're like, oh, it's not there. So like you can like your hand, like if you just get like a few droplets on yourself, like
Oh yeah, that's cool.
right. It doesn't. The dangerous side is like the pooling because it is boiling.
Yeah, but it's not hot.
Yeah, but it's boiling.
It's like so cold and stuff.
Yeah, it's fun to watch like it like travel because you can like see
Whoa,
the
yeah.
droplets.
Whoa.
It looks like they're like alive.
That's
And they
crazy.
just like
Now they're on the floor.
travel around and then they like eventually evaporate, boil away, right? When it's a boil, that would
We
freeze
should
you.
make ice cream with that.
We will. After the AP test.
Okay. I thought we were gonna do the one with like the bag and the salt.
No,
Oh
we'll
wait, the
this.
balloon's back. So once you take it out, then it just.
The volume will come up.
Oh yeah, because the temperature's just hanging out.
Yep. I'll do it again because if you get enough, you can actually get the balloon to be like as flat as a pancake.
Okay. Thank you.
Yep. See you guys.